So we're going to finish up what we were doing with separable differential equations. So if you let's just go do a little bit of review from what we were doing. We were saying that separable differential equations, I'll go all the way back to the beginning, are equations that split the f of xy into functions that are specifically one that only involves x stuff and one that involves y stuff. And so we went through several examples, and then we were down here with some applications. And so the first application we were doing was radioactivity. We said the rate of decay, which is dy dt, is proportional to the amount of radioactive nuclei present. That was y. We said it was decaying, so we know dy dt has to be negative, so our function will be decaying. And we went from here and we solved for what the solution would look like for that problem. Okay, so this is where we were. So this is the solution dy dt equal to minus kt, where y of 0 is 0. Okay, so then we were talking about, let's say we have a substance and after a particular time, half of the substance is still existing. So we called that the half-life. So we said that the half-life, we found the half-life, and the half-life last time was equal to the natural log of 2 over k. So we were just getting ready to do one application. We said scientists who do carbon-14 dating often use a figure of 5,730 years for its half-life. Find the age of a sample in which 10% of the radioactive nuclei originally present have decayed. Okay, so we're looking to see how much they gave us some information. They told us that the half-life is 5,730 years. So from there, we can find the decay constant. If we know that t is equal to the natural log of 2 over k, then that implies that we can find what our k is. Our k is going to be the natural log of 2 over t. I'm sorry. Oh, I'm being silly. Yes, they tell us over t. And so that's right, over t. And for us, t is 5,000. So we end up getting that our k is going to equal the natural log of 2 divided by 5,730. So that's our k. It's very small. It takes a long time. This is a very small rate of decay. Okay, so now we know what our k is. So now for any general problem, we know y of t is equal to whatever the amount present was at the beginning times e to the minus kt, and this value right here, this is our k. So this nice long number is what goes in for k. Okay, so now they tell us that 10% has already decayed. So that means how much is still left? 90%. Okay, so we have 90% of the original amount is still left. And that is equal to the amount that we would have at any time t. So therefore we get 0.9 is equal to e to the negative kt. Now let's take the log of both sides. The log of e to the negative kt, and we already know log of e and log and e are inverse functions. This just gives me minus kt. So therefore, t, which is going to be now negative natural log of 0.9 divided by k. Okay, so that gives me that t equals negative natural log of 0.9 divided by this k that we have. So this is the value of k. All righty. So this specimen is approximately 871 years old. Okay, so for us, t is approximately 871 years. So that's how old the specimen is. Okay, any questions about that? Hopefully you looked at that over the weekend before you came back to class. And so you are right on point in understanding where we are. Okay, I have one more example from this section. This is the example I had originally started to do. This was the application of Newton's law of cooling. Okay. All right, I'm a little thrown off for first. Oh, that's why, because I'm still on there. Okay. Nope. Not right. Okay, Newton's law of cooling, another application. All right, so we have something like a ball. The example I'm going to use is a hard-boiled egg, but something gets immersed in a surrounding medium. So we have an initial temperature of the object, then we have the temperature of the surrounding medium, and then we have the temperature of the object, which changes over time. So T is the temperature of the object, TS is the temperature of the surrounding medium, and T naught is the initial temperature of the object. Okay, so Newton's law of cooling follows a particular rule. And here is the rule. So the rule is that the rate of change of an object is proportional to the difference in temperature of the object and its surrounding medium. So here's the rate of change of the object, that's dt dt. So that part is the rate of change of the object. So the rate of change of the object's temperature. So that's dt dt. And it's proportional to the difference in temperature of the object and its surrounding medium. So that's this part, the difference in temperature. Okay, so now I can solve this just like I did the other separable differential equation. Okay, if we remember, we're going to be able to write dt over d little t is proportional. So that means there is a constant k times the temperature of the object minus the temperature of its surrounding. Okay, so now if the temperature of the surrounding is bigger than the temperature of the object, then that makes this negative and this negative, which makes this positive. So if the temperature of the surrounding is greater than the temperature of the object gains heat. Okay. And if the temperature of the surrounding is less than the temperature of the object, then this item is positive, this is still negative, and this is negative. So if the object's environment is warmer or the temperature is higher than the temperature of the object, it will lose heat. So this represents the model, and K is the diffusivity. Every element, depending on what it's made of, has a different diffusivity. Okay, and the bigger the K is, the faster it's going to lose heat. All right, or lose temperature. Okay, we have an initial condition. We said T of 0 is going to be whatever the object's initial temperature is. Okay. All right, so let's solve this as a separable differential equation. I'm going to take D capital T and I'm going to divide by the T minus TS. Remember, TS is a constant, and that's going to equal negative K, and I'm going to bring the DT up. So now when I integrate both sides, okay, on the left-hand side, I get the natural log of the absolute value of T minus TS. And on the right-hand side, I just might get minus KT plus a constant, nice and simple. Now we said if we want to get something, we want to solve for T, I'm going to take E to the natural log of T minus TS. And then that is going to equal E to the negative KT plus a constant. And if you remember from last time, whenever we have this, we write this as E to the negative KT times E to the constant, which E to the constant we make equal to yet another constant. Okay, so this thing we're going to make equal to a constant. So therefore I get the natural log of T minus TS is equal to A E to the negative KT. Now it's interesting here, again, T minus TS, this is the temperature of the surrounding medium. We're going to allow that to be the positive value and A reflect if it's negative. So we're going to get T minus TS is A E to the negative KT. And so now I know that T is equal to TS plus A E to the negative KT. Now, are we done? That's my question. Are we finished solving for T? How do we know we're finished solving for T? Are we finished? Come on, somebody help me out. Okay. Remember I said, if you have an initial condition, which we do, so we have this initial condition right here. Whenever you have an initial condition, you are not done until you've solved for all the constants. So I have to figure out what that A is. So now we know that when T is equal to 0, capital T of 0 is T naught. So therefore we get T naught is TS plus A E to the 0. Okay, that's simple. So I now get that this thing right here is just A. So now I get A turns out to be T naught minus TS. Okay, so now everything's solved for. So T of T is equal to T naught, that's wrong, is equal to TS plus T naught minus TS e to the negative KT. All right, any questions about that? Okay, so let's use that to solve this fun problem. So we have a hard-boiled egg. It's 98 degrees Celsius. It's put into a sink of 18-degree-Celsius water. After 5 minutes, the egg's temperature is 38 degrees. Assuming that the water has not warmed appreciably, how much longer will it take the egg to reach 20 degrees Celsius? Okay. So we're assuming that although this egg is losing heat to its surrounding medium, because the water is so massive, it's really not going to change temperature. Okay, any ideas about how to start this problem? Can anybody tell me what 98 degrees is? I have T, I have T naught, I have TS, I have a couple things. Can anybody tell me what this 98 degrees is?
Is that the initial?
Okay, so the hard-boiled egg starts off at 98 degrees. Awesome. So T naught is 98 degrees. Okay. And it's put in a sink of 18-degree water. What is that?
TS.
TS. That's the temperature of the surrounding medium. The water is 18 degrees Celsius. Okay, so it says after 5 minutes, the egg's temperature is 38 degrees. So that says T at 5 is equal to 38. Okay, so I think I have a problem here. T at 5 is 38 degrees. That's equal to TS, which is 18, plus I'm going to have T naught, which is 98, minus TS, which is 18, e to the negative. Oh, they gave me T is 5, but what they didn't give me is K. But they gave me enough information to solve for K. So now I get 38 minus 18 is 98 minus 18 is 80, e to the negative 5K. And over here, I'm going to get 20. So I get 20 is 80e to the negative 5K. So now I'm going to divide and get 1 over 4 is e to the negative 5K. And now I'm going to take the natural log of both sides. 1 over 4 is equal to the natural log of e to the negative 5K. So that gives me the natural log of 1 over 4 is going to equal negative 5K. All righty, we're looking at something really good here. So that says K is equal to the natural log of 1 over 4 divided by negative 5. There's our K. Awesome. So now we have a value for K. Okay, so that's the value for K. And then the question says, how much longer will it take the egg to reach 20 degrees? Okay, well, let's see here. We want T at T, whatever it is, to be 20 degrees. So we have 20 is going to equal our 18 degrees is the water, and then 98 minus 18 . I'm sorry, I can't, I need to see whatever, everything I've had. 18 plus, that's right. E to the negative K, and this time we're trying to solve for T. T is our unknown. So 20 minus 18 is 2. So 2 is equal to, this was 80 e to the negative kt. So now I get 2 over 80, or 1 over 40 is equal to e to the negative kt.
I called a while ago.
So the log of 140 is equal to negative kt. So therefore K is going to equal negative natural log of 1 over 40 divided by, oh, we're trying to solve for T, not K. We already know K. Trying to solve for T all over K. And I really just want to go back and double check that I put everything in right. So we said 20 was the temperature. 18 was the surrounding medium, T naught. So that is correct. Okay, so what is this T? Is going to equal negative natural log of 1 over 40 divided by the K that we found. Okay, so that's 13.3. So it takes 13 minutes, and we've already waited 5 minutes. So we are going to get 13.3 minus 5. So we need to wait an additional 8 minutes. .3 minutes. Okay, any questions? Any questions?
I have a question.
Okay, I'm not sure who's talking, but I can't hear you.
It's Dominique.
Hi, Dominique.
So like when we do this on the exam, we're not allowed to have a calculator. So how will we do get the answer into like a number?
Okay, so what you will do is you will leave your K from this problem as, so on the exam, we found that K equals natural log of 1/4 minus the natural log of 1/4 divided by 5. So that's our K. So on the exam, that would be your K. And so for the second part of the problem, notice in the second part of the problem, I didn't use K at all, did I?
No.
Not until the end, okay?
Right.
So therefore, T would be minus natural log of 140 divided by, why do I feel like I'm missing something? No, I'm not. Yeah. Divided by K. So therefore, I would have minus natural log of 140. When I divide by that, I'm going to multiply by its reciprocal. So I'm going to get 5 over the negative natural log of 1/4. So my answer, T, on the exam would be 5 times the natural log of 140 divided by the natural log of 1/4. Okay. Dominique, does that answer your question?
Yes, ma'am. Thank you.
You're welcome. So this is what I would be looking for on the exam for an answer. No evaluation of that, but that's what I would be looking for. Once you find your K, then you find your T, you stick it right in there. Notice only I showed you what the value of K was so that you could get the solution, but on the exam, you won't have that capability. So we will do that. Okay, any questions?